Hello, welcome to another Midnight Maths video. In this one, we're going to be covering trigonometric integration. So this topic isn't explicitly covered in the AP Calculus syllabus, but it is covered in most other calc classes. So this we can handle things like sine cubed x, or cotangent squared, sine squared x, or random combinations of trig functions like that. So the first and probably most important strategy is U-substitution with some setup. Now, luckily, if you know your U-sub pretty well, then this is really just an extension of that. So let's consider a pretty simple example, sine x cosine x. Now, in this case, the solution, all we have to do is just say u equals sine x. And then du will equal cosine x dx. So what happened was we had a cosine x, right? So what the anatomy of this successful U substitution was we had a du part at the end of it, right? Where du was basically the derivative of whatever we want our u to be. And then the rest of the function is only in terms of u. Only in terms of u. So in this case, it was only in terms of sine x. So in this case, we will end up getting integral u du, and from that point, it's pretty straightforward. Now, as long as this left expression is only in terms of u, things are pretty simple, even if the expression is fairly complicated. Like if you have sine cubed x, and then 2/5, right, and then a cosine x, well, you have stuff only in terms of sine, and then a cosine. So when you do the u-sub, everything's going to be okay. We're just going to get integral 2/5 u cubed du. And it's also straightforward to continue. But the part that we introduce here is using the Pythagorean identity. So the main Pythagorean identity we use is this one. And if you're like me and you don't like memorizing stuff, at least memorize this, okay? Because this is with this one you can at least derive the other ones. All you have to do is divide by cosine squared x, and then so for this one you'll get the one involving tangent. 1 equals secant squared x, or if you choose to divide by sine squared, you'll get the other one, which is 1 plus cotangent squared x equals cosecant squared x. Now we're going to use these identities to help with the u-sub. So let's consider, for example, sine cubed x dx. So what we do first is we set aside what we want our du to be. So if we chose sine x as a sub, then we want cosine x. But if we chose cosine x, then we're going to want a sine x. And this minus sign, that's okay. We can deal with that, right? Now, this goes for whatever u-sub you pick. But the four main choices of u are what I've written down here. And basically, these four statements by themselves are just derivatives rules, basically. But keep in mind that if you want to do a u-sub, then you have to set aside one of those du's. I forgot some dx's here. Depending on what you pick, whether you pick sine, cosine, tangent, secant. So in this case, we're going to pick sine. So it'll be sine squared x, sine x dx. And now we have, so we have the part of du part. Great. But now the part that usually can kill the u-sub is if this part. So in this case, we have stuff in terms of sine, but we actually want stuff in terms of cosine, right? Because since we have a sine here, that's going to correspond to this one. We're currently targeting the cosine. Well, that's what we use this guy for, right? So we say, based on that identity, we're going to get 1 minus cosine squared x, sine x dx. From here, we can just make the u-sub, where u is cosine x. And at this point, going to sort of stop here. Oh, we do need a minus sign though. Keep that in mind because this is actually minus du. So that minus sign I put there. So at this point, I'll stop because the remaining integral is pretty straightforward to compute. But the main thing to take away here is using this Pythagorean theorem along with the sine squared to basically just shift everything away from sine because we want cosine. And if you want to use this, then we just shift everything away from cosine and make sure everything turns sine. Okay, so, but does this always work? Answer is no. For example, similar looking, but evidently pretty different problem. Sine to the fourth x dx. So we can try, we can try setting aside this sine 3x, but now we're going to have our du, but we're not going to have our expression that's only in terms of u, which in this case we're still gunning for cosine. So we could say, oh, well, this sine cubed is, so sine cubed x is sine squared x sine x. Now, the real issue is we only work in units of 2 because the Pythagorean theorem relates the squares of the sine and of the cosine. So we could say, okay, that becomes 1 minus cosine squared x sine x. And at this point, you still have your sine x here, and any attempts to solve for sine x are certainly going to run into some like domain issues or something like that. So at this point, we're sort of stuck because we can't get the setup that we need for U-sub. And so this is where our second technique comes in, where we do power reduction. So remember, our first technique, U-sub, it worked great for these odd powers of sine and cosine. And by the way, this works just as well for tangent and secant as well. Just make sure you know what you're putting aside. But the main thing is, like for sine and cosine at least, you want it to be odd because then when you set aside one, when you set aside this sine x, you're left with even, only even. So then it's pretty easy to convert all the way to cosine. But when you have some more even powers, things you start with power reduction. So they're basically just two formulas we use here. So we use sine squared, 1 minus cosine 2x, or we use cosine squared. That's 1 plus cosine 2x, cosine 2x over 2. So we can retry sine to the fourth x dx with this in mind. So basically we just keep applying the power reduction formula until we get something that works, so that we can deal with. So we do, okay, well, I see a sine squared here, so let's rewrite it in this slightly weird but useful way. And then we can just replace, instead of sine squared, we're just going to copy that, squared dx, and then expand, usually lots of expanding, so 1/4, and then 1 minus 2 cosine 2x plus cosine squared 2x dx. So these two terms are straightforward. We're just left with this term. So we use it again. We use this guy. So we go ahead and we say 1/4. Okay, let's just copy this. And then this cosine squared 2x, well, it's almost this formula. Okay? But that, what I just copied down was only for cosine x. But for cosine 2x, well, we just replace x with 2x. 2x. So 2 times 2x becomes 4x. 4x dx. And now it's pretty straightforward to continue because you just have cosines left. And you can deal with that with the U-sub. So generally, power reduction for like even powers of sines and cosines. So now, in principle, using these power reduction formulas are, like these two, it can work, like for example, even if we tried integral sine 10 x dx. It can work. It's just that it's very, very time consuming because you see we went from sine 4 to cosine 2, and then we applied it one more time. So imagine we're going to have to apply 5 times. 5 times apply. And remember, we're going to accumulate these 2x's, 4x's every single time we apply it, just like we did over here. So it just gets very tedious. So usually, one way you can deal with this is by using reduction formulas. So here, I've pasted some formulas for sine, cosine, tangent, and secant. And basically, if you have, like, for example, integral sine 10x dx, clearly these formulas won't just solve the integral for you, but it will help make it a little bit easier, because now you can say n equals 10, so we're using this top guy. And then afterward, we just basically tell us, so if n is 10, n minus 1 is 9, and n minus 2 is 8. So now we just replace those. So the minus sine n minus 1, 9x cosine x over n, which is 10, plus n minus 1 over n integral sine n minus 2x dx. So great. So we got one term, but now look, we have a sine 8. So what we'd have to do is then use this again for n equals 8. So yeah, reduction formulas are quite nasty, but keep in mind that just because these formulas may be given to you doesn't mean you have to use them, right? Like, for example, if you were given sine 3x dx, it might be just faster to just do the u-sum, right? So don't just like use these formulas as a sort of catch-all for anything involving sine, cosine, tangent, secant. Okay, now the final method here, so this you could call this another method. I'll call this 2a, because really these reduction formulas sort of help you do the power reduction. But the third method here is like using other trig. So there are more trig identities other than the Pythagorean ones, and they can in fact help you out. But the two big ones are this one and this one. So with these, you should be able to get around most problems, hopefully. But for example, let me show you one example here. This one, which does, in fact, I'm reading this here, cosine 4x to the 3/2 dx. Does look quite intimidating, I have to say. And if it was just 1 plus 4x, things would be quite nice, and we could move on with our lives. But we have this quite nasty 3/2. So what do? Well, one way we could do it is to say, okay, so we know that the 4x is going to be, so integral of that, and then leave the 1 here. And then the 4x is going to be cosine squared 2x minus sine squared 2x. Because, well, this formula is only for cosine 2x, but if you want cosine 4x, then we just say cosine 2 times 2x. So now we just replace, so wherever we see an x, we write a 2x minus sine squared 2x. So that's what I've written over here. 2 to the 3/2 dx. Haven't we made it more complicated? Well, we do have this 1 sitting here, and I do have my Pythagorean identities. And actually, I also did this a similar trick in one of my other limit videos, where we sort of just write the identity like this, plus cosine squared 2x. It doesn't exactly matter whether you say sine squared 99x plus cosine squared 99x, just as long as these two are the same function. So at this point, you can just say, okay, well, sine bye-bye, sine bye-bye, and then things sort of clean up very nicely. Because this is going to be a 2 cosine squared, 2x. 2 cosine squared 2x, all of this to the 3 halves, dx. And then things become better, because what happens is this becomes a 2 root 2, and then cosine squared, and then to the 3 halves is just going to be cosine cubed 2x dx. And now look, we have an odd power of cosine. So we would continue by using U-sub. And then, so it's going to be cosine squared 2x, and then cosine 2x dx. And now, instead of cosine x, well, first, see, we have the cosine x split off, because we're teeing up for sine x. We want to convert this to only sine x's. So, in this case, we just say equals all this stuff. Instead of cosine squared 2x, and say 1 minus sine squared 2x. And then the cosine 2x dx sits here. And now we can say u equals sine 2x, du equals 2 cosine 2x. And for at this point, we're going to get a simpler integral, right? I'm going to stop here, because what's going to happen is this cosine is going to go away, and the 2 is going to go away as well, and then the bounds of integration will change, because we're going to enter the du world. And then this is really going to be something like root 2 1 minus u squared, right? And this is an easily integrable polynomial. So this is pretty much these three are the big three. With trig, though, there is kind of a mixed bag, in that there are other things that you can do. For example, for some problems, actually, integration by parts, or IBP, works. And by the way, trig is a great example of integration by parts, where you can use the tabular method, which I covered in my last video, to speed up integration by parts repeatedly. Because usually when you're doing integration by parts with trig functions, if you use it, you're probably going to have to use it more than once, as a rule of thumb. Now, the classic example, which I'm going to go over in my tabular method video, so I won't cover that here, but it'll be secant cube x dx, right? And what we do is we say u is just going to be the secant x, and then bv will be secant squared x. And then if you do some grinding, you grind through it, eventually you're going to have to solve. This will appear again, and then you're going to have to solve for it and all that. But just a heads up that sometimes IBP does actually show up in these trig integrals. But for now, we are going to stop at these three. In another video, we might do a little bit more examples, sort of work all the way through. But in the meantime, until then, I'll see you guys in the next video.